Hi, good afternoon. I'm Tony Mastriani, and this afternoon I'm going to talk about taking 3D IC heterogeneous integration to mainstream. I'd like to start first by defining a chiplet, and I like to define a chiplet as an IC that has been designed and optimized to be integrated into a package. Now, traditional homogeneous design, namely where you have a chip that is put into a package, is a well-established process, and there's really not a lot of interaction that happens between the package design process and the IC. It's pretty much once the IC is done, you do the package design, and that's it. When we talk about heterogeneous integration, putting multiple chips in a package, it's a much different problem. You're involved in taking a system or a subsystem, decomposing that into different chiplets. You have to worry about thermal interaction. You have to worry about signal power integrity analysis, many different things that need to happen. And all of this needs to happen concurrently. So the approach is quite different than traditional IC design. So it really is a system type of approach. And we use the term system technology co-optimization. And this really has aspects spanning from architectural planning and analysis, where you're taking a system, decomposing it into chiplets. You have to worry about the functionality, so there's simulation, functional verification, and such. You need to worry about how you're going to test that. So you need to include test structures within the chiplets. You also need to develop and plan for a testing strategy to test the entire system and package, and where you don't really have access to those pins. So all that is part of the planning process. The next thing you need to worry about is the specific technologies that are going to be used to implement each of the individual chiplets, because with heterogeneous, you're not limited to using a single ASIC technology. So you can use many different fabs to implement each of those chiplets. So the other thing you need to worry about is the packaging technology. So as you're doing your system decomposition, those are factors that may impact which way you architect. Can I get away with a silicon interposer? Do I need to do an organic interposer to keep the cost down? Do I do 2D, 3D? So there's a lot of other non-architectural type of factors that need to be considered when you're defining how you're going to decompose your system and implement that as a 3D IC. And then the next step, you really start getting into the physical design. But again, there's a lot of other things that need to be considered that are not normally considered during the normal ASIC process. You need to worry about things like thermal, because you have these chiplets right next to each other, and they can heat up each other, so you have to worry about that. You have to worry about mechanical stress. When we're putting large silicon interposers on an organic substrate, their heat coefficients, thermal coefficients of expansions are different, which means that you can have warpage. So that needs to be simulated up front. So a lot of this thing we'd like to do up front before you actually start dedicating the implementation. So we use the term predictive analysis, where as we start having models and digital twins of the components in the package, we can start doing some of this early pre-layout or predictive analysis. So we can do things like thermal analysis. We can even do signal integrity analysis. So we want to make sure we make all those decisions up front, because we're not dealing with one ASIC, we're dealing with multiple ASIC designs happening concurrently. So the cost is very high. So we want to make sure we're picking the right architecture and implementing that. And then, of course, we get into the detailed implementation of each of the chiplets, the physical design of the interposer, the substrate design, and that happens concurrently as the chips are being designed. So these chips need to plug and play together using high-speed interfaces, die-to-die interfaces, such as UCIe Express and HBM. So the package designer is putting together the floor plan, if you will, of the system and package. So they need to work very closely with each of the chip designers to make sure that these different interfaces are aligned properly. And then we have to worry about electrical analysis. This includes things like signal integrity analysis. These are for the high-speed internal interfaces, the die-to-die interfaces, as well as the external interfaces, SerDes, DDR, and such. and thermal and stress analysis is also. So really there are 5 key areas: the physical design, we have electrical analysis, we have reliability analysis, and then test. That starts up front in the planning, but also as you deliver your parts off for manufacturing, we have to generate test factors, both for the individual chiplets as well as the complete system in package. So what I'm going to be talking about is really what kind of design enablement or design kits are required to support this heterogeneous 3D IC design process. So there is a group within OCP, it's called the Chiplet Design Exchange. And this group is comprised of EDA vendors, fabs, OSATs. These OSATs do the testing and assembly, substrate, material providers. So we do have a very broad set of users that are actively participating in developing, and the charter really of the group is to promote a chiplet ecosystem. So we're looking at things at defining models that are necessary to support the design process, as well as the different types of design kits that are required. So if we look at some of the guiding principles that we have is historically the package design community, the way that they work with design kits is quite different than ASICs. So ASIC technologies have very well structured design kits and PDKs and such, but the package community, not so much. So one of the things we're trying to do is, and the other thing is, we want to develop and leverage existing standards for these formats. So there are formats that are required and different design kits that are required. So if there's existing standards, we want to include those. We do want to make machine readable formats rather than having PDFs, which have been used throughout the ASIC and more so in the packaging side. We want to put these models and design kits in machine readable formats so they can be consumed by the tools and the workflows. And then we also need to have supported workflows. So we need to have the designers, we need to have the EDA companies supporting these different formats. And then last but not least, the manufacturing, the OSATs, the foundries who are generating the data for these different design kits, they also need to be part of this ecosystem. So some of the recent activities that we've done in the CDX exchange group, we started this out back in 2021. We published a white paper, and what we did is we said the first thing, if we have a chiplet, what are the design models that are required for that package in order to integrate that into a package? So we came up with a list of recommended lists, and I'll go through that list in detail. And there's a white paper here, so this is a good reference that you may want to read through to find out kind of the motivation behind how we came up with that recommended list of white papers. And there was another white paper we did also in 2022. And that list, actually, we started working with the JEDEC group. The JEP30 part model was designed to describe electronic components that would be used in a PCB design. So we said we're trying to do a similar thing here in 3D IC, but we'd like to extend that model to support chiplets. So we worked with JEDEC and came up with that list of chiplet design models that are recommended to be included with a chiplet. With the idea is that we could eventually have reusable chiplets out in the marketplace. And that's what we're really trying to promote in the CDX group. And we did get that extension to the JEP30, the part model, that was done back in January of 2023. So that is now a JEDEC standard. Again, these are the models that are required for a chiplet. We also started working on a white paper that talked about the design flow, and it's a very detailed document. It's over 100 pages that gets into a lot more detail about the high-level workflows that I referenced earlier. But what we're actively working on is 3DKs. These are 3D IC design kits. So I'm going to talk about what is in these design kits and how they're used in the design process. Okay, so design enablement. So as I mentioned, the IC design process has a very structured, well-defined design enablement. It includes IP. This is the building blocks that are used within system-on-chip designs. And we have process design kits. This includes the technology rules, the necessary rules for creating extraction decks, place and route decks, etc. And there's also macros that are supported for memory and analog signal type designs, reusable building blocks. So we're trying to extend that concept for a lot of the things in the packaging world, but it is a different type of set of design kits that are required. So 3D IC design requires a comprehensive set of design enablement kits to support the actual design, verification, and handoff to manufacturing. So the goal here, we call them 3DKs for short, and we have different areas listed out here on the right. So the CDK I just talked about, and I'll go through a little more detail of what's in there. That's done, that's an existing standard. What we're actively working on are package assembly design kits. So these are the rules to define the pitch, the spacing, the type of connectivity components that are used to connect these chiplets to the interposers to the substrate and such. So rather than having a PDF file with these rules, it's in a machine readable format. And it's also EDA neutral. So this way, for the different tools, EDA tools that are required to use these assemblies and do the checks and et cetera, we can have one source for these rules, and then each of the EDA vendors, assuming they're supporting these formats, would then be able to take those rules from a single source. So it's going to make it much cleaner access for the fabs and the OSAT, the manufacturing, so they can provide these rules in one format, and then all the EDA vendors can use it. And also, there's by having access to that information in these machine models, they can be used directly for scripting and some of the tools directly. Another area is material design kits, and this really is a novel idea. So when you're doing the analysis, whether it be thermal, stress analysis, signal integrity, power integrity analysis, you do need to have it define the material properties that are in those package components that are inside the package. And again, rather than having that information ad hocly, derived from the vendors, the material providers and such, and then manually put into the tools, the idea is to put that in a machine readable format. We call it a material design kit or an MDK. And then the tools then would take that material information directly for doing the analysis. And then the last one is for test. So we call it package test design kits. So in the chiplet model, we have a lot of information in terms of the physical dimensions of the device, also the pins and the functional mode. But when you're testing these devices, there may be, and typically there is, a different set of pins that are used to test for wafer sort when you're actually testing the wafers. So we are defining the location of those pins, the modes, the physical location, and the shapes, and all those geometries. Those are included in the PTDKs. So this is basically a high-level summary of what we include in the CDK. We can see we have thermal models, we have the different test IEEE standards that are used for testing the chiplets, as well as the 3D protocol for doing stacked, the IEEE 1838. For signal integrity analysis, we have IBIS models. .lib models are used for static timing analysis, and then CPM. So these are all standards, and most of these, as you could see, are existing standards, whether they be from JEDEC or IEEE. One area where we did not see existing standards was in some of the physical models, as well as the electrical models. So this was an effort that was developed in the CDX group. We called it CDMXL, and these have since become part of a JEDEC standard as the JEP physical model. And this includes the physical X, Y, Z dimensions of each of the chiplets. This would include the location of all the pins, the shapes, a definition, whether it's a a copper pillar, a micro bump, a lot of detailed information that's going to be required for the design, assembly, as well as the analysis. And then on the electrical side, essentially we have a lot of an electronic data sheet, if you will, that describes the functionality of the chip, different test modes that are available. We also include in that JEP30 standard, we've taken almost all of the high-speed interfaces, whether it be external, things like DDR, PCIe, SerDes interfaces. So we've taken the standard pin naming from those standards and included that within the JEP30 part model as well as the die-to-die protocols. So UCI Express, BOW, and HBM are the primary ones in use today. And the idea is those can be used to map a specific chiplet pin to those protocols, and they can be used in different portions of the workflow. So all of these models are what we call the CDKs, and these are the recommended chip models that are necessary to support. Now, the remaining slides will talk about the we'll start with the assembly design kits. Now, in heterogeneous integration, you can use different silicon technologies for each of these chiplets. So in this example, we have two technologies. We'll call it Fab 1 and Fab 2. Now, each of these fabs will have a set of manufacturing rules, and what we're focusing on really are the micro bumps or the pins that are used to connect the chiplet to an interposer or perhaps if you're doing 3D to another chiplet. So each of these fabs will have their own set of rules. There may be min and max pitches. There may be min and max bump sizes. So if we're going to have two different fabs working together in the same package, we need to come up with a common set of rules that overlap both of those fabs. So we create kind of a little Venn diagram where these overlap, and there would be a common set of assembly design rules that would be captured for all these chiplets that are going to be used in this package. So then we need to worry about the interposers. So that certainly needs to support the bump pitch that's defined on the chiplets, and we also need to worry about the micro bumps, which are on the bottom, to make sure they're interfacing with the substrates. So we also need to get the substrate vendors involved, and as well as the OSATs, because we need to make sure that they can assemble these as well. So really, the idea is to look at all these manufacturing rules and come up with a common set of rules for use to build and define the connectivity for the chiplets, for the interposers, as well as the substrates. And then the additional information that will require are different constraints and guidelines. So we're providing a format, a structured format, where these constraints and guidelines can be defined, as well as the assembly stack, how each of these components within a package are located and how they're assembled together. And they're very flexible, so you can create custom rules, you can put whatever you choose and guidelines in there. So these are used to actually in the assembly process. It's used for the physical design and verification of the different components, the chiplets, or at least the top level pins and connectivity on the chiplets, the interposers and the substrates. And then this information could also be used to create the EDA specific decks for doing the checks, the DRC and the LVS checks and DFM or whatever. And then they would ultimately be used for the physical verification. So, reliability analysis. This includes primarily thermal analysis that I mentioned earlier and thermal mechanical stress. So here, the material design kits will include the information necessary for that. You need that for each of the components. The substrates, the interposer, PCB could even be included. TIM materials. So the electrical properties would be defined here for signal integrity analysis. For thermal analysis, you need to worry about thermal conductivity, Young's modulus, and all of this stuff. So that's how these design kits are used in the what we call the reliability analysis. Electrical analysis, this includes signal integrity analysis, power integrity analysis, IR drop, EM, electromagnetic analysis, and even STA. So all of these different electrical analysis flows do require extraction. So we have to worry about the having the material properties necessary to set up those extraction decks to do the extractions. And then as we go through each of the analysis, we use information in the chiplet design kits, as well as the assembly design kits and the material design kits to actually go off and run the analysis. And then the last workflow that we talk about is 3D IC tests. So here, the package assembly design kits would define the I/O locations. So this, again, is carefully coordinated between the test teams, the DFT teams, the chiplet designer, and the package designer. And then once those test pins are defined and located, they're put into this machine-readable format, and that can be used to go off and build the test hardware and such. We also have embedded analytics that are included in the chiplets, so we can provide that information as well in these package test design kits. So the next thing I'm going to talk about is the JEP 30 part model. As I mentioned, the CDK, these two models were developed as JEDEC standards, and those are the required models that are in the part model. But all these other models that I mentioned, the recommended models that are required to support the design analysis, we have a checklist. At a minimum, we have a checklist to know what models are available. So if a chiplet designer or a chiplet provider, they can define which of these models are available. So there's different options for each of these. There's also provisions where we can actually include the models, and that's really up to the chiplet provider if they want to include that in the part model. Another really benefit of the part model, and one of its targeted purposes, is to enable a chiplet market system. So here, chiplet suppliers, they can define a chiplet, and if they want to offer that into the market, they can describe all this information that's available, and then the end users and designers can decide, which of those chiplets that can be put into an electronic catalog, if you will, and then your users, your system designers, and chiplet consumers can then look through that catalog, and actually you can actually do business transactions as well. So the chiplet suppliers, again, this gives them the ability to define essentially the information about their products in an electronic catalog that the designers can then look at the different parts that are available and choose the ones that are best suited for the particular design. And then the models actually can be used for the design and verification for the process, and eventually to hand that off to manufacturing. So there are other standards out there. So JEDEC and OCP is driving these 3DKs, but there's also an initiative that was initiated by TSMC. It's called the 3D Box Alliance. All the EDA vendors are included in that. So this is really a TSMC ecosystem, but it is a general usable format. And there is quite a bit of similarity in some of the models. So the package assembly design kits, what I've defined in the 3DKs includes a little bit more, but some of the physical information, the stack up for the chiplets is defined in 3D blocks as well. It's a different format, so the plan is we would have bidirectional translators for some of these PADKs as well as the test design kits. And then the CDKs, really the physical type information, is also included in 3D blocks. So the idea is that if these formats are available, they can be used for the design process. If we're doing a design that includes TSMC, we can generate the formats necessary to provide to TSMC. That is a requirement for them. If you're designing a 3D IC chip, you need to provide these formats to them. So we will have interoperability between these standards. The other thing that we're looking into, and I can't really talk a lot about the details of and the timing, but there is a need to have an authoring tool to create these models. The 3DK models are in CDX format. It's not really a friendly format for someone to type. So the idea is to have an open source EDA neutral authoring tool. And we do have plans that we'll be talking about that. And the idea is we can have a single tool that will create each of these models, and then the specific EDA vendors and manufacturers and assemblers would then use the EDA specific implementations to create the decks and et cetera. So just at the end here, the Innovator 3D IC are the workflow solutions that Siemens EDA is offering into the marketplace. And you can get much more information on our website, as well as talking to our sales and marketing folks to get more information about the tools and the workflows that we are supporting. Okay, I thank you for your time.